Okay, picture this. You're listening to the smooth, soulful wail of a saxophone. Then you hear your own voice echoing back at you from a massive cliff face. And finally, you hear the rhythmic, pulsing beat of a talking drum. On the surface, these seem, well, completely unrelated, right? But what if I told you that they all actually rely on the exact same invisible, fundamental forces of physics? Today, we're diving into the universal science of vibration.
Welcome to this explainer. We're going to look way past the surface of our favorite songs and the everyday noise around us. Together, we're going to uncover the fascinating, invisible symphony of sound waves and vibrations that literally dictate everything we hear.
So here's our roadmap for today. First, we'll explore the physics of musical instruments. Second, we'll dig into the math behind the music. Third, we'll look at echoes and their real-world uses. And finally, we'll wrap things up with a quick pop quiz.
All right, let's kick things off with Section 1, the physics of musical instruments.
You know, when you really think about it, every instrument we play is basically just a machine designed to manipulate sound waves. And they generally fall into three families, each using a different physical material to generate those uniform vibrations we call music. We've got wind instruments, which use resonating air columns, stringed instruments, relying on vibrating strings, and percussion instruments, which use plates, rods, or membranes that vibrate when you strike them.
Now, what's really fascinating here is how we physically interact with these materials to set them off. Take strings, for example. Think of the continuous friction of bowing a violin versus the sharp, sudden action of plucking a guitar. Both of these actions cause the string to vibrate as a whole, sure, but they also cause it to vibrate in smaller loops at the exact same time. And that's what produces both the primary, fundamental note and those richer, layered overtone frequencies.
As for wind instruments, well, you've probably done this yourself, just blowing over the top of an empty glass bottle, right? You're creating sound by forcing air to vibrate over an opening, which is exactly how an organ or a flute works. Other instruments use vibrating lips, like a trumpet, or a vibrating reed, like a saxophone. They're all just using fixed air columns, or columns altered by pressing keys, to create specific resonant frequencies.
So here is the absolutely crucial takeaway. When we're dealing with strings, the resulting sound isn't magic. It is strictly physics. Whether you're tuning a simple sonometer in a science lab or a massive concert grand piano, you're really just tweaking three specific variables: the length of the string, the mass of the string, and the tension, the force keeping it taut. Alter just one of those three and bam, the frequency of the sound wave changes immediately.
Moving right along to Section 2, the math behind the music.
To really grasp this invisible sheet music that governs the universe, we have to start at the baseline, and that is the fundamental frequency. Simply put, it's the absolute lowest note a wire or string can produce when it's fixed at one end and allowed to vibrate. Think of it as the core identity of a sound before all those complex overtones get layered on top.
And this brings us to the universal wave equation. Now, don't let the algebra intimidate you here. It's actually beautifully simple. It just states that the velocity of sound, v, is equal to how fast the wave vibrates, its frequency, f, multiplied by the physical length of the wave, which we call lambda. It is literally the master key to understanding how sound travels.
And the difference between closed and open pipes is a brilliant illustration of how this math applies to wind instruments. Closed pipes, they only give us the odd harmonics, the fundamental, the third, the fifth, and so on. But open pipes give us the whole shebang, a much fuller spectrum of both odd and even harmonics. Because of this, the actual mathematical formula to find that fundamental frequency changes completely depending on whether the pipe is closed at one end or open at both.
All right, let's step outside for Section 3, echoes and real-world uses.
Sound doesn't just travel in a straight line from an instrument to your ear. It interacts with the whole environment. Imagine standing at the edge of a steep canyon and just shouting into it. That distinct repetition of your voice is an echo. It's just sound waves traveling through the air, hitting a hard reflector like the cliff face, and bouncing right back to you.
But hey, echoes aren't just for fun tricks in a canyon. We actually harness this phenomenon of sound reflection for some pretty serious scientific and industrial stuff. I mean, we use it to navigate submarines with sonar, to catch speeding cars and speed traps, to prospect for oil deep underground, and even to calculate the actual speed of sound itself. It's a real game changer.
So, how do we actually determine the speed of sound using an echo? We just track its journey mathematically. The wave travels a certain distance, let's call it x, to the wall. Then it bounces back, traveling that exact same distance x again. So the total distance is 2x.
By plugging that into our standard distance over time equation, we get 2x equals velocity times time. By just clocking how long the echo takes to return, we can easily solve for the speed. It's honestly that simple.
Okay, time for section 4, pop quiz. Test your knowledge. Let's see what you've picked up.
Let's see how much of this invisible orchestra you've absorbed today. Question 1. Think back to our chat on percussion instruments. When a drumstick physically hits the membrane or the skin of a talking drum, what exact mathematical motion is taking place?
Did you guess vibratory motion? If so, you hit the nail on the head. The membrane doesn't just move randomly, right? It undergoes very specific vibratory motion to produce that distinct musical note.
All right, question 2. This one's a classic physics brain teaser. Imagine a bell ringing continuously inside a sealed glass jar. Now, if you use a vacuum pump to suck all the air out of that jar, evacuating it completely, the sound of the bell gradually fades until it goes completely silent, even though you can still see the bell ringing inside. Why does that happen?
Well, it's simply because sound waves are mechanical. They absolutely require a physical material medium to transfer their energy. They need air, water, or solid objects to bump into. So without any air molecules left inside the jar to actually carry that vibration, the sound literally ceases to exist to our ears.
Okay, last question. For this one, I want you to think about how tightly packed the molecules are in different materials. We've got gases, liquids, and solids. In what order does the speed of sound increase across air, water, and an iron bar? It goes air, which is actually the slowest, then water, and finally, the iron bar is the absolute fastest. Because the molecules in a solid iron bar are packed so incredibly densely together, the vibratory energy of the sound wave races through it much, much faster than it does through the loosely packed air molecules around us.
To wrap up this explainer today, I want you to consider this. Whether it's the reed of a saxophone or the taut skin of a drum, the whole world is just a complex, beautiful combination of uniform mathematical vibrations. Everything you hear is literally physics in motion. But if sound requires a physical medium to travel, it really begs the question, what other invisible waves are passing through the silence of space, completely undetected by our ears? Listen closely to the world around you today and never stop questioning.